Oh, nice.
Well, I want to welcome you to Sequoia Park Zoo. Looks like we got a great crowd. Appreciate you coming out tonight. My name's Gretchen Ziegler. I'm the zoo director here. And I want to thank you to our sponsors, Papa and Barkley. They sponsored this lecture series now for, I think, the third year. Their sponsorship helps us videotape these, and then we're in the process of editing the current year's lectures to get those up on YouTube. So stay tuned for these lectures this year to be up there. I'm going to go ahead and introduce our speaker. So Michael Furniss is our lecturer today. He's a forest hydrologist and a soil scientist. He works for the Research and Development Branch of the U.S. Forest Service for 33 years. And luckily, he retired from Redwood Sciences Labs in 2013. I'm jealous. Since then, he has been active in teaching about climate change and leading climate vulnerability assessments. Hi, welcome. Nationally and internationally. I think there's this in the back, maybe. So, climate vulnerability assessments nationally and internationally. He has taught in multiple countries of Southeast Asia, India, Taiwan, Peru, Colombia, Ecuador, Israel, Jamaica, Ireland, and Spain. Gets around. He recently led assessments of infrastructure vulnerability for 3 regions of the national forests spread across 10 western states, including the Sierra Nevada of California and the Rocky Mountain and Intermountain regions. He is currently a lecturer at the Forestry and Wildland Resources Department at HSU, teaching upper division and graduate students climate change and land use, and it is the forest and climate consultant to Redwood Coast Energy Authority, and he sits on the boards of the Smith River Alliance and the Trust for Working Lands. He is a longtime member of the Arcata Forest Management Committee. In February, he will teach as a guest professor at 3 prominent universities in Vietnam. So let's give Michael a welcome.
So thanks for coming out. And every time I mention this concept to people, most of the time anyway, they say, shh, don't tell anybody, everybody will move here. And maybe that's a factor, and we're going to talk about implications toward the end. And people do move here, but often people leave as well. And when you talk to them about why they left, it's like, well, it's too cold and wet here. And that's the first clue about what I'm going to tell you about. And maybe I should swear you all to secrecy, so put your hand on your heart. Just kidding. It's one of those open secrets, and you're probably going to think some of this is bloody obvious, and often the relevant obvious is a good thing to focus on. And I put enough of the obvious things together that there's kind of a story to it, and thank you for coming here to hear that. How many of you have been here for at least 20 years? Oh, wow. We're getting to be natives here. How about 10 years? 5 years? Okay, so we have people that really like it here. And so this is kind of the story. And you hear about climate change all the time, and it just gets worse and worse and worse and worse, and I'm going to kill myself. There's a lot of climate despair and anxiety, and therapists are doing really well, and that's the story. And the other one is redwoods are at high risk of extinction because of climate change. And what if I was able to tell you some secrets that neither of these things are really true? And so in teaching climate change and giving lectures like this about climate change, it's one bummer after another. And I don't like that part of it. And I watch my students just sink sometimes when you tell them how bad it is. And when scientists look at this, it gets worse and worse. And I don't know if you've noticed, but the scientists who are normally very reserved, it's an unrelenting bummer, and it gets worse and worse. And the scientists that are normally quite reserved about this are basically what they're saying now is it's okay to panic. Okay, so things are bad. And so that's supposed to be bad. And so the story I'm going to tell you is actually a relative story about how things are here relative to most other places. And it's a little bit like, oh, you get hit by a motorbike, but at least you get hit by a truck. or you got the flu, but at least you didn't get the bubonic plague. It's something like that. It's not like everything is peachy, we're all fine here, you don't have to worry about climate change. You do. And there will be impacts and suffering and loss here. But I'm going to compare that to a lot of other places, mainly to other places just in California. So this is a refuge in the larger picture of California especially. So I'm going to start with some basic climate change stuff before we go into the refuge story. And this is what I have my students memorize. And this is a really good summary. It's warming fast everywhere we look, and the warming rate is accelerating. Everything's going in the wrong direction. It's us, that is, humans are causing this, and we're sure about that. There was a question about it 20 years ago. That's been resolved scientifically, and we're sure that it's us. It's bad, and I say everything is going in the wrong direction, and it affects everything. And there's a few positives here and there, but the negatives vastly overwhelm the positives. So there's a lot of problems with this. And fortunately, this is not a lecture about the litany of problems. And we can fix it. There's plenty that we can do. It's plenty that is being done. It's not time to give up. Some people have given up. Humans are not capable of getting together and fixing this. And there's some reason to think that way, but it's way early to give up. There's lots of hopeful signs. The meeting in Madrid didn't go very well, especially because American leadership wasn't there, which normally pulls these meetings along. But we meet every year as a globe and hash this out, and some really good stuff happening. And there is scientific agreement that it's warming very quickly and humans are causing it. And the scientific agreement is as good as it gets, as good as it ever gets. There's always a few outliers that don't agree with the prevailing theories, but that's the case here is that there's an overwhelming scientific consensus. And that's based not on a bunch of scientists getting together and agreeing, that's based on the literature. And the scientists conclude, based on the literature and the theory that's come out of the literature, that this is the case. And I wish I didn't have to go into this. It's 2019, but there's a particularly American thing of climate denial. Say, well, we don't believe in climate change. It's a fact. And nobody else in the world does that, except the Brits and the Canadians and the Aussies have picked it up a little bit. The Canadians and the Aussies because they have a fossil fuel industry, and the Brits because they're just cranky. But mainly it comes from the US. And it's distressing and it's incorrect. So here's a list of organizations, scientific organizations, that hold that climate change has been caused by human action. And you can kind of read down here, American Society for Microbiology, the Academy of Sciences of Moldova, you name it, and go to the next slide. The Bulgarian Academy of Sciences, the Ecological Society of America, the Geologic Society of America. You can find your favorite scientific organization here. These are organizations that are very nerdy, and all they have is their reputation. And so they would be very reluctant to make a statement that would later be proved wrong. And so that's the degree of surety in this. The next slide. And the next slide. And this list was made some years ago. I'm sure it's bigger now. And so there's a vast number of the scientific organizations in the world, including the American Meteorological Society, the venerable American Geophysical Union, and on and on and on, that all hold that climate change is caused by human action. And then good old NASA. They sent the Juno probe to Jupiter. It traveled 2.8 billion miles over 4.9 years and arrived at within 1 second of the predicted time. So NASA gets things right. They also just very recently landed an 800-pound geotechnical robot on Mars, traveling at 54,000 miles an hour. So NASA knows what they're doing, and they also confirm that humans are causing the rapid warming that we see all over the world. And this is kind of what's going on. They've actually hired some of the same people, and there's a lot of bucks going into this. I mean, if you had several, if you have maybe $20 trillion worth of asset, and somebody told you that you shouldn't sell it. You might also be looking at what could I do to make sure that I can sell it, and that's what's going on. And next slide. It's easy to deny climate science, and that's what's happening. That's why so many in America, it's a shrinking number of people, but it's still a very significant number of people. Basically, greenhouse gases are invisible. It's long range and slow, it's subtle and complex. You have to have a statistical view to understand climate change. It's confusing, and it's easy to sow doubt and confusion, and people tend to turn away from things that are confusing. And it disproportionately affects people who are not me, my kids and grandkids in the future. When we talk about 2100, how many of you expect to be around in 2100? Yeah. Some will be here, maybe. And it's a risk for us, because I'm going to tell you how we have it easy here. And it is indeed inconvenient. Who doesn't want one less thing to worry about? We all have lots of things to worry about. Somebody says, here, you don't actually have to worry about this. It's like, I'm going to go with that. Who does not want to feel guilty about driving and flying? I don't. And there's a cultish political adherence to denial. And that's a really unfortunate thing that became politicized. And if you're a good Republican, you're supposed to deny this. Plenty of Republicans don't, by the way. For example, good old Arnold Schwarzenegger, but many others. But there is sort of a litmus test, and it's a really unfortunate thing. And it won't last. It can't last. Science sort of wins the day in the end, but and that's happening. And then we see it and feel it here less. So that's what we're going to go into. And we do have sea level rise here. We're coastal, and that is an impact that we know is happening. It's happening now. And we have a really good vulnerability assessment that was done by Alderon Laird and Jeff Anderson. And this is the dikes and the artificial shoreline that fail in the North Bay at 1 meter of sea level rise. And we have a pretty good reckoning on how that works now. And I just wanted to let you know about something that happens on the coast that I think maybe many people are not aware of. We basically have this long, giant wave that's about 140 meters high or 460 feet high, and with a period of about 100,000 meters. And that's the glacial interglacial periods. And this is them laid out in a million-year time scale. And this is an interglacial period when it's warm, and we're in one of those now. And the last one was about 120,000 years ago. And then if we zoom in, and then these are sea level plots. Okay, so sea level is like a big thermometer on the Earth. And basically in the cold periods, sea level is another 440 feet lower than it is today. And if we were in a high ice period or a peak ice period, the coast would be another 6 to 10 miles offshore. All that would be dry land. And that has happened many, many times in Earth's history. You say, well, this is too long a period to even think about. It's not, really. This is a very short period in the geologic time scale. And then here again is the last, let's say, 140,000 years. This is that last interglacial period, the last time it was warm. Sea level was about 8 meters higher than it is today. The Eemian period. Then it got cold and colder and colder and colder. About 20,000 years ago was the ice maximum and the sea level minimum. Sea level was way, way lower than it is now. And then it started warming. That period was ending, and it warmed very, very fast. Sea level rose very, very fast, and then it leveled off. And this is an amazing plot that you could spend your life trying to figure out what the implications of it are. By the way, sea level leaves a lot of evidence, and so these data are good. And so here's that ice maximum, and then here's sea level rising very, very quickly. People had to keep boogieing off the coast because it kept getting inundated. And then look what happened. About 7,000 years ago, it just stopped. And there's been little fluctuations along here, but basically we have a stable sea level in the last 6,000 to 7,000 years, which is huge. And we assume that that's the way the ocean is. Actually, normally the ocean doesn't behave that way. Normally it's rising and falling with great regularity, and along with that, a rapidly changing climate. And so we've had a stable climate and stable sea level for about as long as we know have a history. And it probably was responsible for the development of civilization, that you could build coastal cities and stay there and develop that civilization. So it's just really an interesting thing. And then this is what it looks like when you have a low stand, when ice is maximum, and there's a whole lot of ice tied up in these giant continental ice sheets. And then this is what it looks like when you're at an ice minimum, like we are now, and what's called an interglacial period or a warm period, and the high stand of sea level. And then the amazing thing is that this has been basically a stable line for 6,000 to 7,000 years, even though that's not normally what the Earth does, even without anthropogenic climate change. And there's a lot of consequences to sea level rise, and this is the worst place. Basically, this is king salmon and Fields Landing, and it already floods there at king tides, and they're sort of used to being wet there, but at a certain point before long, that may become untenable to live there. But I've spent some time in the Mekong Delta in Vietnam. There are 20 million people that live there, and they live, a lot of them, right up against water's edge like this. And there's 50,000 king salmons in the Mekong Delta. And they really they stand to lose everything. As people are used to living with loss because they live right at water's edge. But once the salt comes in and the water rises enough, they're going to have to just move and go somewhere else. And that's one of the reasons climate change is a huge environmental justice issue, is there are literally several hundred million people who are very poor, they're oppressed, they're colonized, they're in bad shape, they don't have a lot of money to adapt, and they're in the way of this phenomenon. And the next. And I also wanted to mention, just while we're on sea level rise, that there's an interesting factor that this is an inundation zone for 2 meters of sea level rise with the mean monthly tide. And this same zone is pretty much the same zone for a tsunami hazard, and also the same zone for the hazard of land subsidence in a megathrust earthquake. The big earthquakes, normally the land goes down, and it would be at about this kind of magnitude, 1 to 3 meters. And so this same zone of vulnerability works for sea level rise, tsunami inundation, and large earthquakes. And then this is really the big story of sea level rise, is there's 7 meters of sea level equivalent in Greenland and 57 meters of sea level equivalent in Antarctica. And so really the big story is these 2 big continental ice sheets. The glaciers in the mountains are the poster child of climate change, but they're only responsible for less than half a meter of sea level equivalent water. So most of the water that's tied up in ice sheets is in Greenland and especially in Antarctica. And understanding what's happening to Antarctica as far as melting and disintegration of the ice sheet is smack in the middle of climate research and what's going to happen with the ocean. And there's a lot of uncertainty there, and there's maybe some tipping points that we should worry about. And then if all of the ice melts, which scientists believe won't happen for hundreds of years hence, but we're heading in that direction. This is what happens in Arcata. This is the inundation zone. And it's just an elevation line. And next. And then this is South Arcata.
Is the blue line where the water would come, that would become the coast?
That would become the coast,
Okay.
yeah. And you don't have to worry about that, but maybe our great-great-great-great-grandkids will be looking at something like that if we can't stop the degradation of the atmosphere and halt the increase in heat capacity of the atmosphere. And then there's another process called ocean acidification that isn't climate change, but the carbon dioxide that is the main culprit, not the only one, in terms of increasing the heat capacity of the atmosphere. It also causes an acidification of the ocean. So the carbon dioxide gets absorbed by the ocean and it turns into carbonic acid, and then you get a bunch of protons running around, and the pH goes down. And so the global pH was something like 8.2 10 years ago, and now it's 8.1. And this also deprives the shelled animals of the carbonate that they need to build their shells. And so there's a lot of uncertainty about this. Keep your fingers crossed that this doesn't turn out to be as bad as it could be. Because if this turns out to be really bad, kind of all bets are off. And it was supposed to be a good story, wasn't it? Sorry, but you have to go through these things. The worst case scenario is the shellfish can't live anymore, and most of the ocean food chain is tiny shellfish, plankton, and you can forget about your clam chowder. Yeah, collapse basically, and if the ocean collapses, then everything collapses. Okay, next slide. And then there's a sense of urgency, and there is a great urgency. And the urgency is to control emissions as soon as we can. We're blowing past these targets of greenhouse gases to the atmosphere, and the heat that is generating or will generate in the future. And so as soon as we can do that, the better. There's a great urgency to that. However, in terms of climate collapse, you may get the feeling that all hell's going to break loose in 5 or 10 years. And that's not really how climate change works. It's slow, statistical, fits and starts, happens, then stops happening. It's a slow process. And we're really worried about what happens in our children's lives, much more than what's going to happen to us now. So we're looking at 2030, 2050, 2100. We see it coming. It's all going in the wrong direction. But you need not worry about it's going to turn into a hellscape in 10 years. It's unlikely to happen. There are some tipping points where it could really accelerate, but still, if you look at the papers all the time, sometimes the journalists exaggerate, or they don't understand the process, and so they kind of make a big deal out of it, and you might conclude that we're at this great tipping point and you can write off the world already, and that's not really true. So don't freak out about the climate collapsing anytime really soon. You should freak out about controlling emissions. So California is really an extreme place. The state is extreme, especially in terms of drought and drying. Many summers we have almost no rainfall for 4 or 5 months. It gets crazy dry. And even without climate change, California can have mega droughts, droughts that last really a long time. And tremendous drying. And so they call it the Golden State, is it's desiccated in the summer, and that what goes with that is fires and all the rest of it. So it's basically a very extreme place. And then lots of variability here, tremendous variability. The little difference a month makes. This is what California looked like November 17th. We had some rain here, but the rest of the state was still dry as a bone, still in very high fire danger condition. The rain had not showed up, and people were starting to worry. Fortunately, the rains came, and they came statewide, and this is what it looks like just the other day. And so that kind of variability is California. And so this is what I'm going to go through with you, and I'll go through each of these in detail, but basically temperatures are moderated, moisture is abundant, we don't depend on snow, we don't have tropical cyclones, more fog is likely to happen. I know everybody's excited about that, right? Yeah. No high elevations, we have abundant forests, we have less wildfire, and then I will make the case with you that the redwood forests are very likely to persist. Good news. So it's no mystery why this is so. We basically have the largest body of water in the known universe right next to where we live. And it's cold. As you well know, it's very cold where we are. The ocean is icy, as anyone who's tried to swim in it well knows. And our windbreak is Japan. And so there's nothing but ocean for 7,000 or 8,000 miles once you go offshore. And this is really why we're a refuge. And there's some other more subtle reasons, but this is the big reason. This is the obvious one, but it's real. And I think it's a good story. So let's look at temperature. So this is the current mean temperature in the West. And you can see it gets hot sometimes in Las Vegas, kind of expected. And look at us here. Yeah, I mean, we could do a little warming, right? So take a look at this, and then next slide. This is the projections for 2090. And you can see there's this, like, you know, Salt Lake City, welcome to hell, you know, pretty bad. And any of you know Redding? I mean, could we tolerate 5 degrees temperature rise? Yeah, no problem. How about Redding? Could they tolerate 5-degree temperature rise? The roads will melt. They're already sort of topped out as far as how hot people could stand it. So anyway, here we are, and it's warmer, but it's still quite cool. And then in terms of precipitation projections, temperature is easy to project and predict. Precipitation is really hard. Okay, precipitation is really a complex process. It's a threshold process, and you'll notice that the weatherman is usually correct about the temperature and really often wrong about the precipitation. And it's the same with climate models. The precipitation, the estimates go in both directions. So there's like 20, almost 30 different models, climate models that are run around the world by big organizations that are studying this. And all of the temperature projections go in the same direction, all warming. At different levels, but it's all going in the warming direction. For precipitation for any given place, it goes in both directions. So there's a lot of uncertainty about precipitation. However, there are some things that we can say in a general way and in a large-scale way. First of all, the globe overall, when it gets warmer, it gets wetter. Because for every degree rise centigrade in global average temperature, you get 6 to 7% more moisture in the atmosphere. Okay, that's a lot. So if we went up 3 degrees centigrade in global average temperature, we'd have 21% more moisture in the atmosphere. That's really a lot. Okay, so overall the globe will get wetter. However, the variability also goes up because of warming and because of the way the heterogeneity of the Earth works. And some areas will get drier, and some areas will get warmer. And what you can easily see here is that the wet areas get wetter and the dry areas get drier. And wouldn't it be great if it was the opposite, but it's not. And so when you look at this center area, this is saying it's going to get a little bit wetter, and then it's a little bit drier here, but when we're in the middle like that, what it means is we don't really know, but the changes will probably be small, and the variability will probably go up. Okay, so, and then this is a projection for spring rainfall. And there's a little bit, shows a little bit of a diminution here in Northern California, but not much. Getting wetter here and drier here. And then here's an important way to look at this. So we're used to a range of variability here. Actually, we have a very variable weather. And if you look first at precipitation, this is the historic range of variability. And it's quite large. Now, this is actually for Oregon. But it's about the same year. But the projected changes are well within the range of variability. And so not a super big deal. However, look at the temperature. It goes way outside the range of variability. Less here than most other places, but basically you get kind of a new world in terms of the biota and habitats and the kind of the place it is to live. So inland Washington becomes more like the San Joaquin Valley, for example. And so temperature is really the big story. And it's why global warming is not such a bad term, even though there are a lot of other climate things that happen from that warming. Temperature is really the big story. And then in terms of snow, this is the recent trace of where the snow fell. And you can see it falls in the upper elevation cold places. Okay, that's typically where snow falls. You can get some snow on the coast, but it doesn't last, and it's actually pretty rare. So, and then this is a pretty good indication of where the snow pack is in California. So it's up and down the Sierra Crest, and it's in the Trinities and the Marbles and the Russians, and the upper areas of Mendocino County, and the upper areas of Del Norte County in that. And this is an incredibly important source of water for California. Now, California has this totally dry summer, 30+ million people, and is the vegetable basket of the world, really. And this is where most of the water is in the snowpack. We have a lot of dams and reservoirs, but there's much more in the snowpack than there is in all those dams and reservoirs. And then California snow is warm and vulnerable. So if you go to Minnesota or Pennsylvania, the snow is cold. And it would take a lot of warming to turn that snow, that precipitation into rain rather than snow, or to melt that snow fast. But in California, it's right on the margin. It's a warm snow, therefore it's a vulnerable snow. Therefore, it's very easy with a little bit of warming to lose that, in that the precipitation changes from snow to rain, and the snow melts more quickly. Okay, so in California, water is a super big deal. It's very, very central, and this is the biggest deal about it, is the loss of snowpack. We have warm, vulnerable snow. It's a major source of California water, and we're losing it. This is a plot from Scripps, and shows 2030. The snow water equivalent is a metric that's taken on April 1st. A bunch of people go up there and make cores in the snow, and they figure out how much water is in the snowpack, and then they report that. Here's how much water we have, or the snow water equivalent in the snowpack that's going to make its way down into the valley or wherever as it melts. And so this is the 2030 value, this is the 2060 value, and then this is the 2090 value. And all that's really left is the the highest elevations in the southern Sierra. Now, the really high elevations in the southern Sierra, that's kind of a cold snow, and that's less vulnerable than the others. But this is a horror story if you're a water district manager, or you're somebody that's responsible for delivering water to people and farms and industry. And they're really freaking out about it, and have been for quite some time. It's really a problem. However, not for us. We don't depend on snow for our water supply. We get a little bit of snow, but snowpack is not a big factor in our stream flow, in how our hydrographs work when runoff happens, or our water supply. So we can have no snow at all, and the Mad River and the water supply that we get from there and other places isn't going away because of a lack of snowpack in the summertime. Okay, so it's another factor of our local resilience. We don't have the high elevations here. I'll also mention that the higher elevation, the quicker the climate is warming. And it's not entirely, oddly enough, it's not entirely clear why that's happening, but the data shows that it's happening everywhere. So the higher up you are, the bigger the changes. Well, fortunately, we don't have a lot of high elevations. We have mountains, but they're not very high mountains. And so that's another factor where if you're in the Sierras, the warming is going to be much more dramatic than it is here. Wildfire is on everybody's mind these days, and you have to acknowledge that we can certainly have wildfires here. We have a lot of forests, and it gets dry in the summertime, and they can burn, they do burn. Every redwood forest you find has evidence of fire, but not anywhere near as much as the rest of the state. The dry areas of the state are far, far more vulnerable and have much worse fires. And we're getting some smoke here from those fires, but we don't suffer nearly as much as the inland areas. And we're actually, I think, starting to get some wildfire refugees here. With the terrible fire season that we've had in the last 3 years, people are freaked out, and some people are moving out. Some people have to move out because their house in Redding or Paradise or Santa Rosa burned down and they have to go somewhere else. And some people are electing to go to a nice, cool place that doesn't burn much, like here. So, but if you look at the projections, here we are now, and these are 30-year periods for the high scenario, and it's really bad, but not here. So, and these projections are actually, there's other projections that are much more severe than these, but fire is a hard thing to kind of suss out, but we are fortunate in not having severe fires here. Our fire danger is relatively low. Redwoods have very low flammability. The bark doesn't have pitch in it, and it resists fire, and we also have the cool, moist conditions that don't favor nasty fire behavior. And then in terms of soil temperature, we have what's called an isomesic soil temperature regime. And so it's between 8 degrees and 15 degrees centigrade. It's kind of in the Goldilocks zone. It's not too cold, it's not too hot. And that's another factor in our resilience. And I wanted to explain to you the difference between green water and blue water. It's very important, and it's quite simple. So when rain comes and falls on soil, it gets fractionated. And a certain proportion of it, it's usually about half or sometimes a little more in this particular exposition at 61%, actually just stays in the soil. It's what's called field capacity, and soils are a big reservoir, and they hold that against gravity. And that's what feeds plants is that field capacity water, or that hum water, or what we call green water. And then there's the blue water that runs off and goes right through the soil. When it's raining hard, you get a lot of this, and that's what feeds the streams and the rivers and the lakes and all that. And so the green water hangs in the landscape, and it's usually half or more of the total rainfall is actually in the soil reservoir. And then the blue water is the stuff that comes off. Okay, so it's good to think about that. And so what about water availability for plants? And you know, as a forester type, you think about, well, we at least want to keep the forest healthy. And if you look at that, our soils hold about 2 inches of water, about this much water per foot of soil. And that's what brings it up to that green water capacity. And then if we say our rooting zone is about 6 feet deep, all we need is about 12 inches of rainfall to fill that green water reservoir. And so that, if we have 12 inches of rain, that's a severe drought here. And so we can have a severe drought here and still fill the green water reservoir. And that's what happened in the big drought that we had a few years ago. We didn't see any forest damage from drought. Now in other places in California, especially in the southern Sierra, it's apocalyptic. They had a green water drought. We didn't have a green water drought. We did have a blue water drought. So you remember the streams were really low and the salmon were in trouble. And so the green water reservoir got full, and there wasn't that much left, blue water, to go out into the streams. The green water gets it first, obviously, and then the blue water. So we don't really have very much drought susceptibility because of this. Actually, it's like we can even have quite a dry year, especially severe drought in the rest of California, but we are likely to have enough water at least to keep our forests healthy and watered through the summertime. So we can see a serious blue water drought, and that can happen, and that's something that we're not resilient to. That can happen here just like it happens in other places. So you can have a blue water drought, you can have a blue water drought without a green water drought. You can't have a green water drought without a blue water drought. You get both of those whenever the green water drought occurs, you can have a severe blue water drought. So, and then if you look at these, this was an index put together of water availability for people, and it's bad, especially in the southern states, especially in the Southwest. Not here. And then one of these amazing technologies that satellites can sense gravity as they fly over, and changes in gravity indicate a change in the water status of the landscape. And so you can actually map the water status, the water that's on the surface and underground with satellites now. It's super cool. And then this is a look at the cumulative water storage during that, including that drought period. This was at the kind of the peak of the drought here, and ooh, look, really, really dry and really kind of a severe situation, including all up and down the Sierra Crest. But let's say not here. Next. And then we don't have flooding and storm surge from hurricanes and tropical storms. And we have some powerful storms, but the storms that really do great damage are the cyclones, the hurricanes, and the typhoons. They're all the same thing, the cyclonic storms. They call them different things in different parts of the world, but we don't have them here. And what's really significant about that, not just that you get tremendous wind and sometimes tremendous amounts of rainfall. Let's go to the next one. This is just showing where they occur. and what we expect to happen in the late 21st century. And basically, we can see it happening now is not an increased frequency of cyclonic storms, but an increased intensity. So more Category 5 and 4 and 5 hurricanes hitting the area. And the next one is what the real problem with these is what's called storm surge. And that's not waves. That's a process whereby the wind, heavy winds occur over a long area of the ocean, and it actually lifts the ocean up and actually pushes the ocean ashore and raises the sea level a lot during these cyclonic storms. And then added to that is the fact that you get very low pressure in these storms that allow the ocean to rise against the atmosphere. The atmosphere has less weight, and the ocean kind of rises up against it, and you get what's called storm surge. And we can have a half a foot and a half of storm surge here. That happens, and you can actually see it. You can go out to the beach that you know in a big storm, and you'll see that the high tide is higher than it's supposed to be, and that's storm surge. Well, in these areas that have the big cyclonic storms, they have lots and lots of storm surge. So in Hurricane Katrina, they had in places more than 20 feet of storm surge. So imagine the ocean coming up 20 feet. And in Hurricane Sandy, it was about 3 meters, 4 meters, and that's what made Hurricane Sandy so bad for New York City. Is it wasn't the heavy rain or the wind; it was the storm surge that came up and inundated the subways and all the rest of it. We don't have these cyclonic storms here, and so we're not subject to this kind of impact. But it's a bad impact all along the eastern shores in the Gulf of Mexico and many other places in the world. And then we're like the Saudi Arabia of wood here. I mean, we have a lot of wood. And this is a woody place. It's a forested place. It's what draws a lot of people here. And we have the kind of the best species you can imagine in redwood. So our abundant forests help in at least 4 ways. And just build it all. There's 4 things, and just build them up. They store carbon for a long time, and they store a lot of carbon. The redwood forests here store more above ground carbon than any other forest on Earth. And the below ground carbon is hard to look at, but we know that that's a very big number too. We don't have those numbers yet. Working on that, but it's very difficult. But the above ground carbon is really, really persistent. And redwoods don't rot, they don't burn much. And so as far as carbon storage, boy, they're just great. They're a refuge for species persistence, to hold on to and recover species. Forests are great. They cool and moisten the local climates. If you go out under a forest area, you can tell it's way cooler than out in the open. And then building with wood is far greener than with concrete and steel. And it has way less embodied greenhouse gas emissions than when you build with concrete and steel. And so that's a really important factor. And that wood that gets used is sequestered and stays sequestered for as long as the building doesn't burn or it doesn't get decomposed somehow. And then what about fog? And so there's a story on the table that we're going to have less fog because of climate change. And a number of us, including Troy Nicolini, who's the ace meteorologist with NOAA here, think that that's incorrect. That there's very good indication that we'll have more fog. And if you look at the papers that say there's less fog, they're very uncertain. They have really shaky data to work with. And they kind of tortured that data until it showed a very weak less fog signal. And then those 2 papers that came out of Berkeley made a huge mistake, and they never looked at smoke. And smoke works the same as fog and also creates fog. And we had an enormous amount of smoke emitted here. At one point, there were at least 200 teepee burners going 24/7. Every mill had one, and they would open burn all their mill waste, and they would actually light the clear cuts on fire as well. We had a tremendous amount of smoke. So there's much less of that now. So, but let's go ahead and build that. Oh, okay, that's good. And then part of what goes on with fog is that we have a very cold ocean. and that creates the coldness that drops the dew point and creates a fog situation, raises the dew point rather. And you say, well, the ocean's getting warmer. Actually, here it's not getting warmer, it's getting cooler. And we're not sure why, but if you look at the climate models, and upwelling is hard, but the upwelling in the ocean where the cold water comes up to the surface is projected to increase. And so a colder ocean is happening, but a warmer ocean may happen, but even if it happens, it's still going to be very cold relative to the temperature of the land. And then what really drives the fog is the difference between the temperature inland and the temperature on the coast. And this causes the air to rise and it pulls that marine layer in, and that's why we get foggy mornings. And I don't know if you've noticed, but the hotter it is in Redding, the foggier it is here. When they have a really terrible heat spell in Redding, you can't use the airport. So that's that difference in temperature between those two, the coast and the inland area, is what drives the fog. And that is intensifying. So it's getting hotter, warmer, faster in Redding than it is here. Okay, so that difference may get warmer here, but it's getting warmer faster in the inland, and that should drive more fog. Now, fog is a complex process like precipitation. It's even less well understood. There's some really good people with the USGS working on this to try and figure out if we're going to lose fog or there's going to be more fog. It's a big deal for, less of a big deal for redwoods than people think, I think, but it's a big deal for how these coastal environments work and how moist they are. But anyway, there's a very good chance of additional fog, and this is just a graphic to show you that the ocean offshore here is actually pretty cold. And then let's go into the redwood story, and there's been a number of warnings, and this is kind of the way we react as people. When there's a threat, we look at the most valuable thing or the thing we love the most and worry about that the most. And redwoods are so valued. Everybody in the world knows where redwoods are, and so revered that we really worry about the redwoods, and we should. And there have been predictions that we're going to lose them from climate change. And I'm quite sure that this is incorrect. And it turns out this is one of the last forest types that we would worry about. There's plenty of forest types that we would worry about and are experiencing very negative impacts, but not redwoods. And let me go through the reasons why that's true. And I lived next door to Steve Sillett I have for a long time, and then I rented a house to his research assistant, who we called the Lorax. Incredibly good redwood biologists, and I check everything with them. This is their conclusions as well. Although they're researchers and they have to be careful about making conclusionary things that they don't have all the data to back up. But I can do that. So, and then just go ahead and build this to the bottom. So the redwoods arose about 120 million years ago. So hominids about 2.2 million years. Modern humans, something like 200,000 years. Redwoods, 120 million years. And guess what? They're still here. Where did they persist? Through all the changes that must have happened in 120 million years. Can you imagine that the climate had a lot of fluctuations in the 120 million years, including periods of low fog? Where did they persist? On the coast. It had to be. So they've been here really, really, really a long time. That's not true of most of the other forest types on the coast. It's not true that Douglas fir, great Douglas fir forests are quite recent. But the redwoods have been here a really, really long time. They tolerate warmth. I'll flush that out for you in the next slide. As I mentioned, less fog. No, it's likely more fog. And redwoods don't require fog to survive. There's a bunch of really nice redwoods in Napa County, for example. They don't have summer fog there. And you can grow redwoods in Sacramento if you have sufficient water. And they're growing in many places in the world where they don't have fog. And in fact, when you get low fog years, what the redwood biologists find is the redwoods grow better. Actually, they're getting more sunlight, they eat sun, less fog means more photosynthate, they grow better. And so this idea that they have to have fog to persist is simply wrong. It's not the case. And it's overplayed, actually. and say, well, they just exist in this fog zone along California, they must need fog. And actually we think that the fog is helpful for seedling survival, but what really controls their range is temperature. They really can't handle freezing temperatures. And so when they get far enough inland that things freeze, the redwoods can't really survive that. We also, so this is another one of those things, is like redwood seedlings are very vulnerable. And they really like having summer fog to get them going. And they may not survive very well in low fog situations. However, there's been some redwoods planted now for a while on the Oregon coast where there's very little fog and they're reproducing by seed. So, wrong again. Anyway, the idea that if we lose fog, we're going to lose the redwoods is incorrect. And in fact, if the redwood range does contract for one reason or another, we can easily artificially expand it with planting, and we know how to do that now. So, and then, of course, we're in temperature and moisture refugia. There's no indication of impacts from the recent drought or low fog period. We didn't see any damage from that. And in fact, the biologists see increased growth in the redwoods when there's low fog periods. And then the higher minimum temperatures increase the growing season. And so not only are the maximum temperatures increasing, but more dramatically, the minimum temperatures are increasing. And so you have a longer growing season, the redwoods shut down later, and they grow more. So, and then I'm not saying we don't have to worry about the redwoods. They're so valuable, and there may be vulnerabilities or processes we don't know about. It's very much worth studying. And the Save the Redwoods League has funded Humboldt State, UC Santa Cruz, and UC Berkeley for climate change redwood studies. And these conclusions apply to the coast redwood, not the mountain redwood. The giant sequoia is a whole different story, and they're much more vulnerable. Okay, and I don't have a conclusion for you on that other than to say this coastal climate refugia protects our coastal redwoods, not the mountain redwoods. Important distinction. And I just wanted to note that here's our current period, and this is that ice maximum, and these scales keep changing. So this is 20,000 years, now this is 1 million years, 5 million years, 100 million years, 500 million years. And this is what the Earth's temperature has done. And when you go back far enough, you go back to maybe 2.5 million years, actually this is right when hominids appeared, the Earth was warmer and considerably warmer. And so redwoods arose maybe somewhere around here. So for most of this period, the Earth was considerably warmer and certainly wetter. And the redwoods survived that. And so the idea that if it gets too warm, the redwoods won't make it. They probably have genes in their enormous genome. They have 9 times as many genes as we do. That will enable them to handle high heat. Probably not extreme cold, but high heat looks like it probably isn't a problem for redwoods. And then there are climate refugia at smaller scales that's notable, and these would occur inland as well. North air aspects, cold air drainage basins, basically places that are smaller scale refugia. And this is important, and there's a number of ecologists and climate scientists that are looking for these, for places where species can persist and we can recover species and can hold species in these refugia areas at these smaller scales. But then we have sort of a coast-wide scale refugia here. And then redwood forests are really ideal for carbon storage. So everybody's looking to trees and forests to sequester carbon and keep it out of the atmosphere. And you'll hear, I'm sure you've heard a lot about, we just need to plant a lot more trees and hold our forests that we have. And I want to make the case with you that there is no better carbon fixing machine than a redwood tree. And go ahead and build this one out. So they grow very rapidly. They go crazy rapidly, actually, and they resist fire. So they can burn, but they don't tend to burn up, and they're very resistant to fire. They fight low flammability, and they resist rot. They have all this heartwood that they've invested a lot in that only one very slow fungus can attack. There's 15 different funguses that can attack Douglas fir. There's one, and it's very slow, that can attack redwood. So they're super rot resistant, as we well know when we use their lumber, or notice how old they get. And that's a function of they don't rot and fall over. Douglas fir can't make it more than 500-600 years, and the rot wins and over they go. Not so with redwoods, probably why they get so old and big. They have, the growth does not slow with age. So the idea that as they get old, they slow down and get decrepit and don't grow as much is incorrect. The bigger they get, the more they grow. And this has been fully confirmed now. So they may get shaded out or something, but basically they don't slow down with age. And in fact, age is kind of an animal kingdom concept anyway. And then you have a massive long-term carbon storage. I mentioned that we have some of the greatest carbon storage in the world in our redwood forest. They don't die when cut. None of the other western conifers do that. You cut a redwood tree and it just sprouts up. They don't die. It's an amazing thing. And so they're super regenerative. They're very likely to persist here, as I've mentioned. They're much beloved. And we have increasing areas of conserved second growth and carbon reserves. And so another factor in this, I'm getting close to done, Richard. The ability to adapt depends on a bunch of things, intellectual and social capital, how much finances you have, the analysis that you can do, and all the rest of it. Well, you have amazing social intellectual capital here, really astounding, and I think that's why a lot of us came here, really. We like the salt water, we like the redwoods, we have Humboldt State CR, and I am certain that higher education is the best way to adapt to climate change. These are the people that are going to be dealing with it, and they need to know what they're doing. And so that higher education is the front line of climate adaptation. We have a world-class energy research lab. The Indian tribes often get it and take progressive action. It's really kind of remarkable how the degree to which the tribes often understand the environmental crisis and know what to do. And then we have people like Andrea Tuttle, Sharon Kramer, Alderon Laird, and Jeff Anderson, and on and on and on. Steve Sillett and all in the Save the Redwoods League studies, and many, many others. And, I hate to be listing things because there's so many people that you could list here, but we just have social capital that is vastly beyond our population. And that enables us to adapt to climate change in a whole bunch of ways. And then we have forest sequestration reserves. The city of Arcata has almost 1,000 acres. The Van Eck Forest, the Yurok tribe has a reserve, and so on. And these are occurring in more and more places where you can get carbon credits, either on the voluntary market or through California's cap and trade market, and get paid to leave that amount of carbon on the site for 100 years. And that's happening all over. And then we have immense carbon accretion and storage in local forests. So when we look at what are we doing for climate change here, well, our forests are doing a hell of a lot for us. And I don't know, go out and thank a tree, and then we have low population pressures. But now that everybody finds out about this, they're going to move here and our population pressures will go up. So population pressures and climate change amplify each other big time. And we're blessed with having relatively low population pressure here. And so just to review this, we have moderated temperature. We have enough precipitation, likely to probably get more. Snow, there's going to be less, but we don't need it here. We don't have tropical storms that create storm surge and really bad episodic sea level rise. We'll likely have more fog. I didn't go into this, but the models don't show that we'll have increased winds. And in fact, some of the winds are de-intensified so far. So that's uncertain, but so far, worse wind is not happening. We have abundant forests. They're cool and they're wet and they eat CO2. The redwoods will probably be okay. We're adaptable. We have huge social capital and robust higher education. However, we do have sea level rise. We have flooding. We'll have blue water droughts. We'll have in-migration pressures. And the family of humans and plants and animals across the globe are going to suffer greatly from this. And so will we, but not nearly so much. And so what are the implications? There's 4 builds, I think, on this. So keep going. And this is the fundamental idea of conservation biology, is you need refugia. And it's a place where you save the best and restore the rest. A place where you can anchor the recovery of species, the places that aren't going to be mucked up as bad as other places. And so refugia are really, really important. And the conservation biology thinking has been for the last about 20 years is that these are the places that you should allocate the least risk. They aren't mucked up yet, so we can go muck those up and stay away from the places that are already really degraded, is kind of backwards thinking. Find the places that are still really good and try to keep them intact. And then in migration, yeah, people will come to the coastal areas, and maybe especially here, when they find out about this. And when it's 4 degrees warmer in Utah, it'll be half a degree warmer here. Now don't hold me to those numbers, but that's the kind of difference that there is from the inland west to the coastal areas. It's dramatic. And eventually, when it's a hellscape inland, people are going to look to be coming here where there's enough water and it's cool and moist. So, and there's a risk maybe for complacency and lack of local incentive to decarbonize. So we're fat and rich and happy here. Why should we bother, dealing with our carbon emissions and getting smaller cars and flying less and eating less meat and all the rest of it? We know what to do, but most people aren't doing it yet. So, and then we don't have as much incentive to do it because we're not seeing the terrible stuff that's happening in many other places of the world. So with that, I'll kind of open it up if anybody has questions or would like to add some implications to the fact that we're Climate Refuge here. So in the back.
So I know this may be a little bit of a funny question to try to answer, but let's just say you have 100 acres and you think, what could I, even as minuscule as it, what could I, like, off the top of your head, 5 things I could do on my 100 acres, maybe not exactly on the coast, but say up in the hills around Nealon or something. What could I do if I had a lot of resources to manage my land and just do some things that make a little difference?
Keep it growing wood would be the big thing. Make it as fire resilient as you can. Probably with just good forest management. And I would emphasize, and you know this, Sam, try to get as much carbon as you can into the soil, because the soil holds carbon really, really well. It doesn't burn, and then carbon from trees can be very long lasting because of the lignin. It forms lignin polymers, and they can last a millennium or more. So, okay.
I remember reading about Alaska waters warming, and there was a connection to the polar vortex in the Midwest, and then the blob that we had off the coast.
Yeah.
So what about the changes in the ocean and the likelihood that we would be affected on it?
Yeah, we may well be affected. The models show that the jet stream is migrating north, which would tend to bring less storms and so we're drier. But there's a hypothesis that isn't worked out yet, but it seems quite tenable that the Arctic is warming much faster than the equator. So as you go north, the warming is much more dramatic, and especially with the Arctic. And so the temperature difference between the equator and the Arctic is what drives the jet stream in a lot of our weather. It's really hot here, really cold here, and that difference drives a lot of the weather and is responsible for how the jet stream behaves. Well, that difference is de-intensifying, is getting less, and the hypothesis is that's leading to a lazier and more meandering jet stream, and one that doesn't shift to the east as fast. And that brought us our drought, and it brought the extreme temperatures to the Midwest, a drought here and the extreme cold temperatures to the Midwest. And it happened when you get these great big meanders in the jet stream. They're called Rossby waves. Then you get extreme weather as a result of that. And the thought is that climate change may be doing that because of the de-intensification of the equatorial polar difference in temperature.
Okay.
Yeah.
How do we know how hot it was hundreds of millions of years ago? And what was alive back then? There weren't humans, but what was alive, and what accounted for this, it's hotter then than it is now?
Yeah. The Earth is still cooling off. It was a big ball of hot rock for whatever billion years ago. And it's been cooling off ever since. And then the way we know how warm it is there's a bunch of indirect indicators. And so isotopes of oxygen, the difference between O18 and O16 tells you the temperature. Going back that far, it gets a little more speculative, but it's pretty well known from a variety of, what the sea level was, for example, or what was alive then and what got laid down in the rocks. For the last million years, however, it was 800,000 years, now it's pushing past 1 million, is we have ice cores that are taken in Greenland and Antarctica, and they take out those ice cores and they've got little bubbles in them that formed when the ice formed. And the ice has seasonal lines on it, just like the rings on a tree. It's not just like, but they're like the rings on a tree, and they can date that ice column to within 2 or 3 years. And then with very careful laboratory technique, they can extract the air from the bubbles and figure out how much carbon dioxide was in them, and then what the O2, O18, O16 ratios were, and they can really rebuild what the climate was. It was 1 million years ago. And so we know for a fact that carbon dioxide is higher now than it was in the last 1 million years. And actually, we're pretty sure that it hasn't been this high since at least 5 million years ago.
Okay.
And that's part of the reason we're alarmed.
Right, because it would still be cooling off, but it's not, and because the hypothesis is
Yeah.
that we humans are heating it up again.
That's right. We have these orbital variations that are responsible for the glacial interglacial cycles. They're very slow, but they should be driving us cooler now, and we're not getting cooler. So that's another line of evidence of why humans are causing this, is the interglacial period should be about over, but obviously it's not.
Yeah, thank you.
Yeah.
Can you speak a little bit about happening in the Arctic with regards to the melting permafrost? I mean, what I read is that most climate models don't account for the melting permafrost or the CO2 level.
Yeah, what's really hard about the climate studies is the atmospheric physics is kind of straightforward. And if you've got this much greenhouse gas, your heat capacity goes up this much, and your temperature, global average temperature should go up about this much. And that's not that difficult for the physics. What's difficult is how it interacts with all the Earth systems, with permafrost, with forests, with oceans, everything else, with vegetation especially. And those feedback systems, some are positive, some are negative, are not super well understood. And so the permafrost melting is a big problem because as it melts, it releases carbon dioxide. I was going to try and not be, but here we go. There's another really bad story, and that is there's a whole bunch of methane accumulating in the Arctic right now, and it's persistent. It's been there for months, and it's really increasing very quickly, and it probably comes from methane hydrates in the ocean, and the warming process in the ocean, and it's releasing methane into the atmosphere. And if that keeps happening, it's very bad. Yeah. So there's these tipping points that can occur where climate change will start occurring much quicker, and we don't know where they are. They're nonlinear processes. They're not very well understood. We can see that they exist, but we can't say when we're going to hit them or how bad they'll be. But permafrost is a tipping point. The methane hydrates are a tipping point. The loss of forests in the Amazon and what that does to the climate overall is a tipping point. There's a number of others that kind of keep the climate scientists awake at night. Yeah.
And the rest of us.
And the rest of us, yeah, in the back.
Yeah, I wanted just to kind of make a point I was thinking about the implications. Like you said, you know, the theory for science is to protect the places that are considered refugees. I don't know if this is comparable to the Amazon, the size of this area here, but it seems like if that is true, that this area is a place worth protecting, what people can do here now to try and make, you know, mitigate some of the things, at least in this area, is really push with our local people for good, excellent land use planning, because if indeed people want to move here as the climate worsens in other parts, and we want to keep the forests and species, there's going to be a lot of tension. And so it seems like what we can do now to make some change is trying to really do some great land use planning and how we're going to accommodate more people and still protect this environment.
Yeah, I totally agree. I'm teaching climate change and land use now, and the land use is a really big part of the climate change picture. It's huge, and right now we're probably a pretty positive contribution, but there's negative pieces of it as well, and so the more we can keep forests growing, especially, and yeah, you're absolutely correct. Well, we got a lot of questions. Get where?
Do you have an idea when we get in trouble, when that is? When is you have
It's affecting everything already. So when you look hard, or in many places you don't have to look hard, you can already see it. There's already trouble. So it's less here, but in other places it's really clear. You talk to farmers, they'll tell you, man, things are not like they used to be. And for example, in these big mega deltas of the world, they're already having big problems. So in the big city in the Mekong Delta called Kanta, it already, when you get high tide and the winter base flow in the Mekong, the streets fill up with water. They get that water this deep. And they just ride their motorbikes through it, and it's just the way it is, but it didn't used to be that way. And so they're right at the edge of catastrophe. And a number of other places are like that. And I talk about the Mekong because I've been there, but Bangladesh and Mumbai and even Mississippi and on and on and on and on are in serious trouble, especially from sea level rise. But also, one of the things that you see everywhere is changes in phenology. Who knows how many of you know what phenology is? It's the timing of organisms' life history. When they migrate, when they show up, when flowers bloom, when the bees come out and where they go, and all of that is called phenology. And that's changing everywhere we look. I'm not a biologist, but when you talk to the biologists, they say the phenology is messed up everywhere. And a lot of times, different species, their phenology intersects. So the insects get there when the flowers are blooming, and they're synchronized. Well, if that gets desynchronized, there's real consequences to that. So we're already in trouble everywhere. And that's right here. Yeah, sea level has risen about this much in the last 100 years, and that's almost certainly accelerating now. So if you lived at water's edge, that's another thing, though, is that we didn't build to water's edge here. And we have infrastructure and highways and various things that we need to worry about, but we don't have a whole bunch of people living in that zone that's going to be inundated. So it's another factor where we're better off than a lot of places. San Francisco Bay, they're not sinking as fast as we are, but they have a tremendous amount of infrastructure that's in the inundation zone. For example, the campuses of Facebook and Oracle and Google and a whole bunch of other big these big giant campuses, they're all at water's edge. That was all that was left by the time everything else was built out down there, so they put them right up against the water, and they're all in the way of sea level rise.